Lesson 1, Introduction to Functions. The concept of a function, ranks pretty near the top of the list of important algebra concepts. Almost all of higher level math, modeling is based on this concept. But the cool thing is it's relatively simple, and you guys talked about it last year in Math 7-8. So it says the definition of a function. So here's our biggie. A function is a clearly defined rule that converts an input into exactly one output. And many times our inputs are our x's, and our outputs are our y's. So we deal with the x's and the y's. These rules often come in one of four forms. They could be an equation, you could see a graph, a table, or a verbal expression. And we're going to see all four of those in this lesson. So the first exercise says, consider the function rule, multiply the input by 2, and then subtract 1 to get the output. So that's essentially a word problem. And we're going to look at a table. So if my input is 0, it says multiply the input by 2, then subtract 1. So what's the output going to be? It's going to be -1. So then if we start that and repeat that with a 1, it's multiply that input by 2 and subtract 1. Do that little mental math and we get +1. And you could do that 2 more times with 2 more numbers. 2 times 2 minus 1, and we end up with 3. And then we could do that again for 3, and we end up with 5. So that's a function in a table. Now, part B, it says write an equation that gives this rule in symbolic form. So we know how to write equations. So we get our output by multiplying our input by 2 and subtracting 1. And part C is going to be that function as a graph. So we're just going to plot these points that we came up with on our table. So 0, -1, I'll write them next to the table. Oops. 0, Oops, let's back that up. I apologize. 0, -1. The next one would be 1, 1. We're going to plot those on this graph to the right here. 2, 3, and 3, 5. So 0, -1, 1, 1, 2, 1, 2, 3, and 3, 1, 2, 3, 1, 2, 4, 5. So we see something like this, and it would continue on. So there's a graph of it. So exercise 2, we're going to talk about, I believe, a different function. It says if the function rule in the function rule from number 1, what input, so now they're going to ask us what x would be needed to produce an output of 17. Why is it harder to find an input when you're given an output than finding an output when giving an input? So what we have to do is we need to sit and think about our equation, y equals 2x minus 1. So it says what input? So we're solving for x. I don't see why they said why is it more difficult. I still think it's pretty easy. So it says if our output, meaning our y, is 17, we'll put a y up there to remind ourselves, and then we take, sorry, I just lost my stylus, there we go, 2x minus 1, we add 1, divide by 2, we end up with an x of 9. So we came out with an an input of 9 when our output is 17. So we just kind of reversed it. Not difficult. A function rule takes an input n, so now instead of x we're using n, no big deal, and converts it into an output y by increasing 1/2 of the input by 10. By increasing 1/2 of the input by 10. Determine the output for this rule. So what I just highlighted in purple is our word problem. It's given our rule. It says determine the output for this rule when the input is 50. When our x is 50, then write an equation for this rule. So it says by increasing 1/2 of the input by 10. So 1/2 of our input and increasing it by 10. That's exactly what the rule just said. So half of 50 is 25 plus 10 is 35. So what would that rule be? The output is equal to 1/2 of the input. They asked us to use n in this problem by increasing it by 10. Okay, so there's our function rule. Go ahead, flip the page. It says function rules do not always have to be numerical. Okay, that's generally what we use most of the time. They simply have to return a single output for a given input. There's our rule. There's our function definition. The table below gives a rule that takes as an input a neighborhood child. So our x's, our inputs are the children, and gives an output the month he or she was born in. Okay, so that's our y. So we have a table here. It's representing a function. Why can we consider this rule a function? Why could we say that it's a function? So we go back to that definition of a function. For each child, which is our input, there is only one month she or he was born in, output. Okay, so it fits that definition. So for each child, which is our input, there is only one month he or she was born, which is our output. Okay, so that's essentially our definition of a function. So it says, what is the output when the input is Rosie? So the input is Rosie, the output is February. Find all inputs that give an output of May. All inputs that give an output of May. So May, we have Zeke. Do we have any more? Yep, we have Nico. Why does this not violate the definition of a function, even though there are two answers? Okay, think about that. Inputs of Zeke and Nico give outputs of May. Cool. This does not violate the definition of a function because each input still only has one output. Each input still only has one output. If we reverse that, it's okay. Okay, it doesn't matter. Okay, there's no condition of functions that insists that each output has only one input. Okay, so it's okay to be the reverse of that. So meaning you can have repeats in this y or this output column. That's still okay. Functions are useful because they can often be used to model things. So in the real world, so we're going to talk about this girl's trip to school, and she has to ride the subway. Okay, so her distance from school in blocks is given as a function of time in minutes. So if I examine my graph, we've got in blocks distance from school and then minutes along the x-axis. 0, we can notice that this is counting by ones, and this is going to be counting by blocks of 2. Okay, how far does Charlene start off? Okay, where does she begin from school? How far? Right here, 22 blocks. What is her distance from school after she has been walking for 4 minutes? So I scan down here. Here's 4 minutes. How far is she from school? So I meet the graph. She is 14 blocks from school still after she's been walking. So now it says, after walking for 6 minutes, so 6 minutes is right here, Charlene stops to look for her subway pass. So she's paused right here. Okay, how long does she stop for? So she stops from 6 to 9. She stops for 3 minutes. Okay, 6 to 9 minutes she stopped for looking for her subway pass. Charlene then walks to a subway station before heading to school on the subway. How many blocks did she walk to the subway? So she found her subway pass and right here she gets to the subway, because we notice what's happening. Her speed is definitely increasing, so she must be on the subway there. So how many blocks was she from, how many blocks did she walk to the subway? So she walked 2 blocks to the subway. Okay. And then it says, how long did it take for her to get to school once she got on the train? So she's on the train here, she gets to school here. That took her from 11 to 15, so it took her 4 minutes. Okay? All right. Nice job, guys. Functions.